the states of matter. As a result of this teaching tutorial, you will be able to, on the honors level of expectation, compare and contrast solids, liquids, and gases. There are actually 5 states of matter, but we will just prioritize 3 in our study of chemistry this year. Could you, if I gave you a sample of matter, for example, a ruler, so we can easily classify this as being in the solid state, but can you defend why is it a solid? If we could draw ourselves 3 boxes, and why don't we choose something we're all familiar with, and that would be water. Each water molecule is made of 2 hydrogens and 1 oxygen. But just for ease, why don't we represent a single molecule of water as a single sphere? If we could get on the molecular level, like a lot of the animations that you did on the instruction page, could you draw what would be different if water is in the solid state versus the liquid state versus the gaseous state? So I'll encourage you to go ahead and pause and make those drawings. Do not worry about being in error. We want to give an attempt. You want to give a good, educated guess. Then what we'll do is talk about some differences between these 3 states, and then go back and do any correcting that we need to do within what you drew. A lot that will help your understanding of chemistry will come through being able to imagine particulate behavior. So again, please pause, and on the molecule level, draw what water would look like in the solid versus the liquid versus the gaseous state. Go ahead and do that, please, and pause me. Now, coming back, I'm going to wait to draw mine. What I'm going to do is talk about how these 3 states of matter compare to each other in these characteristics. Now, the main error that a lot of students make when they come in to their first chemistry course, but that they have a hard time correcting, is they think that liquids have properties in between the properties of solid and gas, and that is not true. Solids and liquids are so much more similar in their characteristics and their behavior. In fact, this year we'll study a whole chapter with solids and liquids together. But gases, they're a little crazy and really are different in their characteristics. We'll actually take 2 chapters this year to dive deeper into trying to understand gas behavior. All right. If you would take a look in a dictionary or the average textbook, they would define the states of matter per volume and per shape. That's all right, but we're going to go much, much deeper. So let's actually start with particle energy. Why don't we start at the bottom? And we're just going to be relative. So how do the particles in a solid compare to a liquid, compare to a gas? And if we think about the animations, so the water molecules in the gas, they had to be contained. That cup that it started with, containing the water molecules, there was a lid on it. All right, and that gets to some of the characteristics of gases. The particle energy in a gas, and we're talking about kinetic energy, the energy of motion, in a gas is very, very high. And in a solid, very low. And a liquid we'll get to in a moment. So, whenever the lid was taken off of the cup of water molecules, the water molecules couldn't even be contained within the bounds of the cup. They've such high kinetic energy. Where solid, extraordinarily low, but they do have energy. Now, if we would draw one solid water molecule, where would we draw the next one? We would draw it touching. In a solid, there's virtually no empty space. The particles are very close. Now, in this case, each particle is a water molecule. So this is water and this is water. They're very close. The particles are touching. There's virtually no empty space. So I would draw the next one here, and maybe the next one here, and the next one here, and the next one here, and so on, and so on, and so on. All right. But especially in the animation of the joint in the bridge, unless matter is at absolute zero, the coldest possible temperature, it has some kinetic energy. So how were the particles in the metal bridge moving? They were vibrating and periodically rotating. They're going to be expressing that energy. So vibrating and rotating in place. All right. But how about the gas? So if we were to draw one water molecule, if we think back to the cup of water in the gaseous state that poured, they were really far away from each other, weren't they? Usually in a gas, one gas particle is about 10 diameters of separation. So really, I probably should have drawn this a little bit further. And why don't we put one way over in the corner here? So particle distance is very far apart. And if you would like to go ahead and say that, it's approximately 10 diameters of separation. Between each. But what about the particle motion? Well, kinetic energy is the energy of motion. And if gases have very, very high gas particles, they are moving in chaotic, random, rapid motion. So if you would think of, sorry for the spelling. If you would think of the, let's see, popcorn kernels in a popcorn popper, they're getting heated, and there's air moving around and so on. Or the balls in a lottery machine, the ping pong balls that have the numbers on them, they're just moving in a chaotic, random, crazy pattern. All right, well, how do we show that? Well, in a comic strip, if someone's chilly, they kind of have these parentheses kind of showing the shaking. But then what if someone's running? Well, don't they show kind of, like this? And I'm going to show these as kind of like moving in this direction. Oh, there's this guy moving over here, so that we can tell they're moving in different directions. All right. But how does a liquid compare? Again, not right in between. These properties so much more similar to solid. So we wouldn't say that the particle energy in a liquid is in the middle or medium. It's actually low. Now, the animation beautifully showed the particle motion in a liquid. The particles exchange places. Whenever particles can exchange places, well, that makes that sample fluid. So if something flows, well, then it's a fluid. And if it's a fluid, that means the particles that make it up, they can exchange places. The solid particles did not. Now, the individual solid cubes, which are made of multiple solid molecules, those exchange places, but not the particles that made up each of the cubes. Okay, so the solid, those don't flow, but liquids and gases do. All right. particle distance. In a liquid, they are barely separated, barely. We still say in a liquid, there's virtually no empty space. There's just enough that they can move around each other. So, how would we draw that? Well, they're touching, but there's still a little bit of space for them to be able to move around. All right. So we want to make sure, okay, I know that just my own drawing, we may be able to say, well, there's some empty space, but we're still going to, do our best to apply and illustrate these. So how do we show kind of motion? Well, I'm going to show like this going over there. This guy's going over there, So some reenactment. This is going to go over there, and this will go over here. It's almost like I wish I could do a before and an after. And I think that's good enough. Okay, so again, these are usually the two characteristics that if you would look up in Webster's dictionary, what is a solid versus a liquid versus a gas, what it would say. All right. Whenever we are describing the volume or the shape of these, we use the term definite and indefinite. Definite means set. Indefinite means can be changed, particularly if you put the sample into a different container. So let's talk about the solid. Now, that's why that first animation was so good to engage with. So when the solid was put into a different container, the volume did not change and the shape did not change. So in a solid, the volume is definite. The amount of space that cube took up was the same in the cup and then in the tray. The shape was the same in the cup and then the tray. But what about the liquid? The volume did not change. If you buy a 2 liter of soda, that is a 2 liter volume of space, no matter if it's in the bottle that you brought home from Giant Eagle, or if you poured it into a bunch of different Dixie cups, or if it's spilled out on the floor. The volume of liquid is set. But we know if we would spill it out on the floor, it would not keep the shape of the bottle that you brought it home with. So just like when you poured the liquid from the cup into the tray in the animation, the liquid shape is indefinite. We know that liquids take on the shape of their container. However, they do not fill the entire volume of the container. That's what gases do. Because gases have indefinite volume and indefinite shape. If we would have a balloon, and that balloon, whatever was containing the gas got broken, we know the gas would expand to fill the entire new container, maybe the room, and it would take on the shape of that new container. Okay, but why? Why all these properties? Okay, here's where we get to the true honors application. This is all in good. But ladies and gentlemen, if you on a test told me what made a solid is because it has definite shape and definite volume, I would say, give me more. That is a 7th grade definition. Honors chemistry student. What makes a solid is the relationship of particle attraction and kinetic energy. What makes a liquid, same relationship of particle attraction and kinetic energy, particle attraction and kinetic energy. Well, kinetic energy, energy of motion. And we already talked about very low, low, very high. But what is this particle attraction? Okay, so I will just abbreviate particle attraction, PA. All right. So I know we just, wrote one water molecule as a sphere and another water molecule as a sphere. There's attraction between water molecules. I know that you have seen water molecules on a counter collect and make a bigger water molecule. I wonder if you've added drops and they make a bigger they wouldn't do that unless they were sticky. That's particle attraction. What is the force that is pulling these, or pushing, we'll talk about this more as the course develops, these together? What is holding one water molecule to another? They're sticky, so imagine them as like lumps of clay. Now, it doesn't matter if water is in the solid, the liquid, or gaseous state. The particle attraction is dependent upon the composition. So it depends on the composition, what the substance is made out of. If it's made out of two hydrogens and oxygen covalently bound, it has a set amount of attraction. That's constant for your substance. Okay, so the particle attraction of water is always the same. So whatever value we're assigning is the same for solid, is the same for liquid, is the same for gas. So let's just arbitrarily call it 10, a value of 10. Now I just pulled that out. I'm not going to assign a unit or anything, just a stickiness of 10. Now you could have other things that have stickiness of, 20 or 100 or less, but we'll just say it's 10. Now, again, the particle attraction is constant no matter the state because it's based on composition, and it's water, water, water. Well, the question is, what is the kinetic energy in comparison? Water molecules want to hold each other together, but what is the kinetic energy in comparison? Well, what did we say here? Why are gases so crazy? Why do they have indefinite shape and indefinite volume? Because the kinetic energy is much greater than the particle attraction. This is probably like 500. So even though the water molecules want to stick, they can't because the kinetic energy is so high. So they will naturally move away from each other because the kinetic energy is so much higher than the particle attraction. They naturally are as far apart as their energy will allow them to be because the kinetic energy is greater than the particle attraction. Well, what about a solid? Why does it have a definite shape and a definite volume? Well, the kinetic energy is lower than the particle attraction. So this is finally where the water molecules can stick because their energy of motion is so low. But what about a liquid? Well, that's where they're pretty balanced. So, what makes a liquid? There's enough particle attraction to deliver a set volume. Enough particle attraction that they have a definite amount of space they take up. However, there's enough kinetic energy that they'll take on the shape of their container. That's why they have an indefinite shape. Now, they don't have an indefinite volume because the particle attraction is limiting. But in a gas, the particle attraction is not limiting. Now, in a solid, the particle attraction is of the greatest. It's showing itself in full display because there's just very little kinetic energy. Maybe this is 1 or 2. So, the different characteristics that we talked about are really based upon this relationship. Now, we will keep revisiting this the entire year. This really is what makes the difference and is the expectation for how honor students explain and apply our different states of matter. But we will revisit this again and again with bonding and with phase changes. So this is just the start. We will practice. I know your first hearing can be overwhelming. See about the questions that I'm going to expect you to be able to answer after this video. Go back and rewatch anything that you need to. What we need to be able to do, remember, ladies and gentlemen, is to compare and contrast So if you're asked which of the states of matter have indefinite shape, indefinite volume, can you answer that? But that's, pretty elementary. If you would be given a particulate diagram, could you classify what state of matter it is? Can you defend if I would say you have something that you classify as being a liquid? Why? Can you teach this to another student? Best of luck.